All right, let's get started. So today we're here to discuss the EfficientNetV2 paper. I'm not feeling the best today, so bear with me. And I also thought we'll do things a little bit differently this time. So rather than um, having a pre-annotated version for the paper and then just going through that part of the paper, I'll actually show you on how I go about reading a new paper, and then we'll go through the abstract first, and we'll go through the introduction, read the conclusion first, and pretty much just I just wanted to show you in the process of how I read this how I first read this EfficientNetV2 paper, and then we'll go deeply into everything that's being mentioned in the paper. So my setup is a little bit different today, but should still be good for everybody. So can you guys see my screen as well?
Yes, we can see it.
Okay, awesome. Cool. So then as part of this, the first thing I'm going to assume as we go and we start looking into the EfficientNetV2 paper, I'm going to assume that we all know about what efficient nets are. So that's EfficientNet V1. I'm going to assume some of that. I'm going to assume you have some background in CV, so you know about what a ResNet is or what a bottleneck block is. But in saying so, I'll be giving some brief introductions to each of these, including bottleneck blocks. And as we go through, I'll be providing context for everything. So with that being said, let's get started. So in terms of when we look into the EfficientNetV2 paper, there's when I first read this paper, there's actually not a lot of things that are very new or very innovative. So when I say it's not very new and innovative, what the authors have done is that they took the existing excellent ideas. So they took excellent existing ideas like, progressive resizing and the next one is again a fused NB-conv. So we look at what these are. But these are the two main things: progressive resizing and then fused NB-conv. So these are both from before. I think progressive resizing was first introduced in 2018 by Jeremy Howard and Fast AI team, and then fused NB-conv has been there since 2019 as part of the Edge TPU. So EfficientNet V2 is basically an improvement on EfficientNet V1. So they pretty much thought there's some things wrong with EfficientNet V1. They looked at the disadvantages, they looked at where things are slow or what's missing with EfficientNet V1, and they said, okay, let's release V2. So with that being said, let's get started. So then again, as I said, things are a little bit different today. We'll read this paper as I go. It's not going to be, I'll not just look at some parts of the paper, but the whole paper. And then if we have time, we'll also have, if there's time and if there's interest, then we can also look into the source code of EfficientNet V2. That's something, again, that's a bit different in this paper reading group than in the past paper reading groups. So the first thing then, as I go, first thing I read is the abstract, and I go very quickly into reading about the abstract. So the main thing is this paper introduces EfficientNet V2, and then it's faster training speed, better parameter efficiency, all good so far. To develop these models, they did some things like neural architecture search that has also been part of EfficientNets. So EfficientNet V1 had neural architecture search. And then the next thing that they said is we use new basically operations such as fused NB-conv, which we'll look into in a bit more detail. And then finally, they developed this EfficientNet P2, which is faster than state-of-the-art model. So they don't say which state-of-the-art model, and it's 6.8x smaller. But the question is 6.8x smaller than what, or what is the state-of-the-art model that they're referring to right now? But that's okay. I mean, as long as they say that, we'll believe that that's true. Then the next thing they say is we speed up the training by introducing progressively increasing the image size during training. So that's, again, this idea, as I mentioned, is this progressive resizing. We'll have a look at this in a bit more detail exactly as what progressive resizing is. And then the last thing they say is with progressive resizing, efficient V2 significantly outperforms previous models. And once they train it on the ImageNet 21K dataset, it gets 87.3% top one. So then a few things that have been mentioned here that we should look at. The first one is fused NB-conf. The second one is this idea of progressively increasing the image size during training. And then what's this ImageNet 21K? Oh, sorry, also one more thing. If you haven't read what the EfficientNet paper is, so that's the first version of, that's EfficientNet V1. So if you go to my blog, I have this blog on EfficientNets that would explain everything about EfficientNets, about what neural architecture search is, what's this idea of compound scaling, and then how does the EfficientNet architecture look like. So in EfficientNet V1, they use something that's called an NB-conf. So we'll have a brief look into what NB-conf is, but for more details, if you're interested, I'm sharing this in Zoom chat. Please have a look and also go about reading this EfficientNet blog. Another thing I want to say, as part of the questions, something, because we're live on YouTube as well, so something I do is we have 1db.me/EfficientNetV2 as the URL. So if I go to this URL, it will take me to this report. And I only monitor the comments on this report. This is something that we've been doing as part of every paper reading group. So let me post this in Zoom as well. Okay, so you should have the two URLs. So as I go through the EfficientNet V2 paper, if you have any questions, then please put a comment on this report. I'll come to this report every 10-15 minutes. I'll have a look at the questions and then answer those questions. But if you're asking questions in the chat, I'm really sorry, but I'm not monitoring the chat, Zoom chat or YouTube chat for that matter. Okay, so then back to the EfficientNet V2 paper. So the first thing is, what is this progressive resizing idea? So what I saw in Fast AI, what Jeremy was doing, which was really interesting, is that when you have a model, the first thing you do is you input 2 to 4 by 2 to 4 images, and then you train it by some loss. If it's a classification, let's call it cross entropy loss. Then you train this model. So this model is now trained for these 2 to 4 by 2 to 4 images. But because in a CNN, in a convolutional neural network, you could just pretty much take this exact same model and then instead pass 256 by 256, keeping the same weights. So the weights remain the same. You could then pass 256 by 256 image size, and then you could fine tune this model on this bigger image size. And then you could do a third iteration where you could pass in 512 by 512 image size. So as you see, as we're training the model, the image sizes are going bigger and bigger. So we started with a really small image size. What are the benefits of having a really small image size? The benefits are it's faster, less computation intensive. So these are the two main ones. And then it's also easier for the model to train because it requires less computation. It's also easier for the model to train with a smaller image size. But when we train on a 2 to 4 by 2 to 4 image size, then the model, if it's ImageNet, so ImageNet has how many? ImageNet has about, I think, 1.4 million images and about 1,000 classes. So what this model, when it trains on 2 to 4 by 2 to 4 image size, what happens is then this model has already some idea about these 1,000 classes. Like if it's pets, then it already knows how dogs look like. If it already knows how cats look like. And then when we increase the image size, then it's actually trying to, then the model accuracy is going to improve. This is again an idea of compound scaling. So when we want to have bigger models, there's like 3 ways of increasing the model capacity. So the first way is you increase the image size. The second thing is you increase the depth, which means you make the model deeper. So if it has 10 layers, it makes it It makes it 20. I mean, instead of having 10 layers, you have 20 layers, which is increasing the depth. And then the third thing is increasing the width. That's just increasing the number of channels. So again, these are just the basics that I assume you would know. But if you don't, then have a look at this, have a read of the EfficientNet blog that I mentioned. And in there, you'll find everything that's been explained. What does it mean by scaling the depth? What does it mean by scaling the width? What does it mean by scaling the resolution? And the EfficientNet paper, what they said is, instead of increasing one thing at a time, instead of just increasing the depth, instead of just increasing the width or the resolution, why don't you increase everything at the same time? And that's what compound scaling refers to. So that's just the abstract. So that's how I like to read an abstract. I just have a look at the abstract and I kind of join the dots with previous papers. So the next thing is, again, a fused NB-conv. I won't tell you I know what an NB-conv is from EfficientNet V1, and I assume you know what an NB-conv is from an EfficientNet V1, but we will look into it together as we go. And then we'll look at what this fused NB-conv is and how is that different from NB-conv. So let's just read the abstract first. That's the very first thing. And then we pay more attention to the introduction. So in introduction, what they say is pretty much that training efficiency is important. So for example, you have models like GPT-3. So GPT-3 is very large, I think about 1 billion parameters, if not more. But it can do things very well, but the problem is it requires thousands of GPUs. And a standard person, especially me, I don't have access to those thousands of GPUs. So if I want to retrain GPT-3, it's actually going to be a problem. I won't be able to do it with the amount of GPUs I have access to, or the amount of GPUs a normal person, unless your Google or Facebook would have access to. So to increase training efficiency, we've already had a look at in one of our past paper reading groups, we had a look at the Nf-ResNets. All that does is that removes batch normalization. So that's just the basic introduction, that training efficiency is really important. And what I mean by training efficiency, or what the paper means by training efficiency, is just this idea that your model should be fast. And what does it mean by the model should be fast? It basically means that if you have images to process, or if you want to make predictions on a set of images, then this model should be really efficient. Like, it should not be too big, something like a GPT-3 that requires thousands of GPUs, or it should not be too slow. It should not take like 10 seconds per image, because then you won't be able to use this model that you have trained that takes 10 seconds in a real world scenario. So that's what it means by training efficiency. And EfficientNets have been, EfficientNet V1 was one of the best papers when it came to training efficiency and also model accuracy. So EfficientNet V1 used this idea of compound scaling, and what that did was they were able to have this really high accuracy while being efficient, but there was some drawbacks. So we'll have a look at the drawbacks. So again, they say in this paper, we again use neural architecture search. If you don't know what neural architecture search is, I will show you just a little bit on what that means. But again, if you go back to that EfficientNet V1 blog, that will have more background on what neural architecture search is and how that looks like. Okay, so now, as I said, EfficientNet V2 looks at the drawbacks of EfficientNets. So that's here. So our study shows in EfficientNets, first thing, training with large image sizes is slow, which is true. Like, if you have a really big image size, 1024 by 1024 or 512 by 512, then your GPU, so if you have a GPU, then this is my GPU. If it has 16, say, gigabytes of, sorry, if it has, is that megabytes or gigabytes? I've just confused myself. It is gigabytes. If it has 16 gigabytes of, Sam, is that a correct memory? Is it 16 megabytes or gigabytes? It has to be gigabytes, right? A standard GPU, B100.
Yes. Yes.
Yeah, I'm just confusing myself. Thanks for that. So anyways, if it has that much memory and you have an image size that's like 1024 by 1024, so that's my first image size. And if it's 224 by 224, so say that's my two options. My first option is having this smaller image size, and my second option is having this bigger image size. If I have this smaller image size, then I'll be able to fit maybe 512 batches. So basically my batch size, sorry, my batch size would be a 512. I would be able to fit 512 images of this smaller image size in this GPU. But if I have a bigger image size, then I'll only be able to fit maybe say 32 or 64. So what happens is when your image size goes bigger, the batch size goes smaller. So if you have 1,000 images, then let's say if you have 500 images per batch, then you actually have to do a lot less iterations, and it's much faster to do training on smaller image sizes. But if you have a bigger image size, then it's actually much slower. So that's what they mean. Training with very large image sizes is slow because there's only so many images that can fit in a batch on a single GPU. The next thing that they mention is this thing about depth-wise convolutions are really slow in early layers. So right now, again, if you've read the EfficientNetV2 paper, you'd know where depth-wise convolutions are used. But that's basically, I'll give you context. So the EfficientNet paper, the architecture looks something like this. So this is EfficientNetV2 paper. This is how the architecture looks like. What's this NBConf? NBConf layer looks like this. That's NBConf. Specifically, NBConf 6 looks like this. So what you have, first, you have a conf. It's like an inverted residual. So what you have is typically you have a conf 1 by 1. It's just like a 1 by 1 convolution to increase the number of channels. So if your input image has, or your input feature map has F channels, then what this conf 1 by 1 will do, it will increase the number of channels from F to 6F. So that's just increasing the number of channels. And then you apply a depth-wise convolution. So this is where a depth-wise convolution gets applied. And I'm just showing you what an NBConf looks like. So this is where the depth-wise convolution gets applied. So you again have an output that's the same as H by, well, same height, same width, but again, 6F channels. And then you can have another convolution layer that will reduce these number of channels from 6F back to F. So that's your NBConf that was used in EfficientNet. Where is this idea coming from? This idea is very similar to a bottleneck block. So in ResNet, you have this thing called a bottleneck block. What's the idea? Let's say your input has 256 dimensions. So your input looks something like, say, 64 by 64 by 256 channels. That's your input feature map. If you try and do a convolution, a regular convolution on this many channels, it's going to be a lot more computation, right? So then what they do is, this is just a bottleneck. So in ResNet, you have a basic block and you have a bottleneck block. This is from the ResNet paper. You have a basic block and you have a bottleneck block. So what the bottleneck block does is it will reduce the dimensions from 256 to 64 by just using a 1 by 1 conf. So then using a 1 by 1 conf, what you have is your number of channels have reduced to 64. And then instead of applying the convolution to these 256 channels, you apply the convolution to 64 channels. So that way, what happens is your computations are less. It still covers the same. I mean, it's just a bit, it's just an easy way of first reducing the number of channels, then applying a convolution, and then again, increasing back the number of channels. So this way, it's much easier to do it this way. And then NBConf is just an inverted way of doing it. It's like an inverted residual block. It was first, I think, it was first introduced in a MobileNet V2 paper. So I'm just giving you context. This is just, we are not discussing the EfficientNetV2 paper right now. This is just giving you context on where these terms come from. What is NBConf? When was it first sort of released? So NBConf was first part of MobileNet V2. From what I've read in the research papers. And then they use something called a depth-wise convolution. So see how this is different from bottleneck block. A bottleneck block was reducing the number of channels from 256 to 64, basically going from F to F by 4. What this inverted, that's why this is called an inverted residual block, is because it's increasing the number of channels. So it's going from F to 6F, but instead of using a regular convolution, they're using a depth-wise convolution. So they're using depth-wise conv. So giving you context again, if we go into the MobileNet V2 paper, this is where it's first introduced. So bottleneck with expansion layer. So if you really want to dig deep into all of these things, go back and have a look at these. This is where the inverted residuals was first sort of introduced, and they're using again a 1 by 1 followed by a depth-wise and then a 1 by 1 conv. So then what is this depth-wise convolution? Okay, so let's say this is my width, this is my height. Let's just call this height, let's call this width, it doesn't matter. And let's say I have 3 channels. So my input is h by w by 3. In a regular, I think if you know what convolutions are, then what you would know is if this is my input image. So an input image is just, let's say I have a 3-channel image, blue, red, RGB basically. So let's just say these are my 3. So my input is h by w by 3. 3 channels being these RGB. Sorry, this is G, this is R, this is B, this is R, and this is G. So let's say this is my input, right? When you do a convolution operation, what happens is your convolution kernel looks something like this. This is H dash, W dash, and then again, this is 3 channels. So this is H, it shouldn't be H dash, it would be K. So if my convolutions, if you're in PyTorch and you say something like nn.conv 2D and you say 3 by 3, that just means that your kernel size is 3 by 3. So let's say this kernel size is equal to 3 by 3. And then it's also a 3-channel because you want to apply that to this 3-channel RGB input. Then what happens is this K by K will get applied to this section of this image. I'm just showing you what a regular convolution looks like. And then each of these elements, they do a convolution operation on all 3 channels together. So you get an output. And then you have n such kernels. So let's say you have n such kernels, then you get an output of 1 by 1 by n just for this part of, because it will be applied to each convolution, and then that's what gets added here. So this output is just this much. That's just a regular convolution operation. How is depth-wise convolution different, and what is the idea behind a depth-wise convolution? What they do is, instead of in a regular convolution, when you do the convolution operation on all 3 channels together, what you do is you separate the channels. So this channel goes here, this channel goes here, this channel goes here. Then instead of having a filter which looked like K by 3, you have a filter that looks like K by 1. So each channel has its own, it's basically a broken up. It's basically like you're breaking up the regular convolution. Instead of doing all 3 channels at once, you're doing 1 by 1 channel. So when you have this kernel of channel size 1, you do the convolution operation with this 1 channel, so you get some output. Then you do this second kernel with this second channel, and then third kernel by this third channel, but each kernel has 1 channel, instead of like in a regular convolution you could have 3 channels or 64 channels or like multiple channels. But in depth-wise convolution, this is how that looks like. And then so you get some convoluted outputs, right? This is your output feature maps. You join them together. So you have, so if this was W dash by H dash after doing this convolution operation, then this would look something like W dash H dash by 3. It's kind of the same output. Like you kind of got it's kind of doing the same thing, but just the operation is broken up. And then you have a one-by-one convolution that will mix the channels with each other. So that's just what depth-wise convolution looks like. And this is how this depth-wise convolution operation is different from a regular convolution. The benefit of doing this instead of doing like a regular convolution, the benefit of doing it this way is that the computation, if you look at the number of multiply addition operations, it's less as you compare it to a regular convolution. So this way of doing this, having a depth-wise convolution, is in terms of the ML ops, in terms of the multiply addition operations, it has less operations to be done. That's so in your head you would think, okay, then that means it has to be faster on a GPU because it has less operations. But what they actually found, what the EfficientNetV2 paper found, is that using this depth-wise convolution is actually slow. So that's contradictory, right? That's very contradictory. The depth-wise convolution is meant to be faster, but then it's slow. Why is that? I'm trying to find the Edge TPU paper. 1 second. Okay, the answer is here. I won't go deep into it, but this is just this paper. This is the accelerator aware neural network design using AutoML, which is the Edge TPU paper. They basically said that the depth-wise convolution. So if you have a look at this, sorry, I don't have this open. Okay, there it is. So then the reason why this way of, like, on your left, this is NBconf. So if you remember, NBconf was just this. You have a convolution 1 by 1, then a depth-wise, then a convolution, right? So this is your NBconf. You have a 1 by 1 convolution, then a 3 by 3 depth-wise, then a 1 by 1 convolution, right? What they noticed is that in modern GPUs, or like the GPUs that we use in our day-to-day lives, what they noticed is that the utilization of this depth-wise convolution is really low. So even though the number of multiply addition operations in a depth-wise convolution compared to regular convolution are less, even then, but the utilization on the GPU is much less compared to a regular convolution. So what that means is when you're actually using this on a standard GPU, the depth-wise convolution is actually going to be slower than rather than if you were just using a normal convolution. So this in turn turned out to be EfficientNet. This turned out to be a bottleneck in the EfficientNetV1 paper, is that we should not use depth-wise like they pretty much found this, that using depth-wise convolution is actually slower than what they thought would be faster. So that's just a bit of background when they say depth-wise convolution. Depth-wise convolutions are slow in early layers. The next thing that they say is equally scaling up every stage is suboptimal. So again, this is compound scaling. This is what they did in compound scaling. I told you that the three ways of scaling are depth, width, and then resolution. And what they did was, previously we would just architectures would just either increase the depth, or architectures would just increase the width, or architectures would just increase the resolution. What they said is, let's increase that all by 1.1x. So the new architecture is 1.1 times deep, 1.1 times wider, and the image size is 1.1 times r. But it's using like the same parameter to sort of scale all three together. And this sort of line, what they figured out is that equally scaling up every stage is not the best way. Like, there should be a different way, that you should probably increase width by 2, depth by 1, or resolution by 0.5. So that's just giving you context. So I'll take up questions right now. If there's any questions on, this is fairly important as we go forward. I mean, the main things you should know are, until now that we've read is that even though depth-wise convolutions have lower multiply addition operations than a regular convolution, in standard GPUs, this is slower, then you should also have right now, if it's okay, that you should have some idea about what compound scaling is. But if there's any questions, I'll take up questions on what I've explained so far. We haven't looked into the EfficientNetV2 paper yet. I've just given you context on what EfficientNetV1 looked like. So let me have a look if there's any questions so far.
Yeah, man, I had a question. I'll just speak it out loud. So, in your practice, how do you benchmark if something like depth-wise convolution is actually working slowly? Because I assume, like at least if I were to use something that's just checking how long it takes to run, it's a lot of functions, right? So, how do you benchmark that?
Yeah. Oh, it's I don't do anything. Ross Whitman has done everything for us. So if you don't know, I use PyTorch in my day-to-day life. So in PyTorch, there's this wonderful library by Ross called PyTorch Image Models. It's also called TIM. So that's the library there. This has a benchmark script. So if you search benchmark. So there's this benchmark.py script. All you can do is then you can pass in your model architecture with depth-wise convolution, or you could pass in the EfficientNetV2. This will tell you like how long the latency is, or what does, like how many images get passed. Then you can actually compare the different speeds. So yeah, so this is definitely a good way of having a look at it. I think there's also some results.csv in here. If I go in results, there's all these different results that there are. So if I have a look at results, ImageNet, you can see what the top error is for what image size, what the parameter count is, and how these different architectures compare to each other. I think there's also one with latency. I'm not sure. I believe there would be one, but this is definitely the way I go if I want to compare speed and um, if I want to check the latency of NBConf. In fact, something you will see, oh, this wouldn't work, search in this, but let me go here. So in fact, the EfficientNetV2 paper, when they were checking the latency, they also used this exact same repository that I've pointed you to. So this is from the EfficientNetV2 paper that we're discussing today. They say, although our EfficientNetV2 paper are optimized for training, they perform well for inference. And since latency often depends on the hardware, so that's exactly what I've said. When we're using depth-wise convolution, even though the number of multiply addition operations are less, it actually depends on the hardware that you're using, what CUDA, do you have the latest version of CUDA, what container you're using. So it also depends on a lot of practical things like which GPU you're running things on. So what they did is we use the same PyTorch image models code base, Ross Whitman, and run all models on the same machine using a batch size of 16. So even they're using the same repository to benchmark how fast EfficientNetV2 is compared to EfficientNetV1. And then they see, okay, compared to the recent ResNest or other papers, EfficientNetV2 achieves 0.6 better accuracy and also 2.8x faster inference speed. So that's the way that I go about it, and that's the way the researchers in EfficientNetV2 have gone about it as well.
Awesome, thanks.
No worries. Does anybody else have any other question? Ops just stand for operations. When I say ML ops, I just mean multiply. Yeah, ML operations. So that's what I know. All of this sounds complex right now, but I've actually made it a really good effort in the EfficientNetV1 paper to give context for each of these things and why NBConf is fast or slow or those sort of things. But so far, the key takeaways are NBConf, which I've showed you, is a 1x1 conf followed by a 3x3 depth-wise, followed by a 1x1 conf. So that's the NBConf block. This is slower than basically a fused NBConf. So I haven't told you what fused NBConf is. So I'll do that next. But what a fused NBConf does is that instead of using this 3x3 depth-wise and a 1x1 convolution, it just says, okay, let me just use a regular 3x3 convolution followed by a 1x1 convolution. So that's what we'll look at next. But that's just the idea, because NB, because depth-wise convolution is not optimized for, I'm sorry, could I please ask everybody to mute themselves? Thank you. Because depth-wise convolution is basically slower on modern GPUs. That's why maybe the faster way to go about it is to use fused NB-conv. The next thing that we have looked at so far is that this way of scaling depth with end resolution of by just using a single parameter and then scaling everything by a same number is not the best way to go about it. So that's the second drawback. And the third drawback is training with very large image sizes is slow, which I said because the higher or the larger image size that you go, the more memory it takes in GPU. And that's why the batch size then becomes smaller. And as your batch size becomes smaller, your training takes more time. So that's the main things that they found. Okay, these are the three main things that we need to fix in EfficientNet V2 if we want to make it better than EfficientNet V1. The next thing they also, this is on top. So not only did they fix these three things that we'll see how they fixed it, the next thing that they also did is this idea of progressively increasing image size during training, which I've already told you looks something like this, that you have 2 to 4 by 2 to 4 at first, and you train your model, then you go 256 by 256, and then finally you fine tune your model on 512 by 512. So you start with the very small image size first, but you increase it after some certain amount of epochs. That's this idea of progressive increasing image size, which has already been introduced by Jeremy Howard in 2018. So that's the main things. Now let me tell you what fused NB-conv is. I've told you what NB-conv is, but what is this fused NB-conv? Fused NB-conv is not something that's new. Fused NB-conv is something that was introduced in 2019. And again, all they did was when in an NB-conv, this is the paper called Edge TPU. So this paper name is Accelerator Aware Neural Network Design using AutoML. And this is a really good paper that introduced Edge TPU. And this paper was actually looking at EfficientNet paper, and they said, okay, let me try and use this on the modern TPUs and see, even though like depth-wise has less number of operations, does it actually mean that it's faster on a TPU? Does it actually mean that it's faster on a GPU? So they try and optimize this EfficientNet paper on TPUs, and they introduce this idea that instead of having these two things, where a 1-by-1 convolution takes the channel size from 128 to 512, and then the depth-wise convolution occurs on this that does from 512 to 512. Let's replace this with a single operation, which is this 3-by-3 convolution that's very much optimized and has a high utilization of 37.7% compared to a 1.07% on the modern accelerators that we use, TPUs or GPUs. So all that they did was replace this with this 3-by-3 convolution, and then everything else remains the same. So this architecture on the right is called, or this idea is called fused NB-conv. This is also called, I mean, in the EfficientNet V2 paper, they call it fused NB-conv. In PyTorch image models library that I showed you, I think it's called the Edge TPU residual NB-conv, something like that. Let me confirm. So something I want to show you is, again, when I mentioned on Twitter today that we're discussing the EfficientNet V2 paper. Ross Whitman, he's the author of PyTorch image models. Again, this is just everything that I've told you so far. He said the same thing. The fused NB-conv has been around since 2019, which is this exact paper. This Edge TPU paper has been around since 2019. And on your left is the NB-conv that uses depth-wise convolution, and then they said it's not very it's not utilizing the GPUs or TPUs very well, so just replace it with 3-by-3 convolution, and it's just called Edge Residual in TIM. Basically, in the same library, it's just called Edge Residual. So anyways, if you want to try all of these things in code, definitely PyTorch image models is one of the easiest ways to go, and that's how I kind of go about it. But the way this paper reading group is different is that I'm trying to as we go, I'm also trying to give context and on all of these things. So it might be a little more complex, but if you're not able to get like if you're not able to get what I'm trying to explain right now, that's also completely okay. Go back, this video will be available on YouTube. Sit on your own time, and then all these references that I'm providing, read the EfficientNet blog, read this, have a look at this PyTorch image models, and then have a look at what progressive resizing, so this idea of having 2 to 4 image at first and then increasing the image size, that's introduced by Jeremy Howard. Like go to this research paper, click on that, and then have a read on what that is. Once you have this sort of context that I'm giving you, it will really help you, and then you'll really be able to understand EfficientNetV2 a lot better. But now going forward, so far, just summarizing what we've already looked at so far. We've already looked at what NBConv is. This uses depthwise. We know that it's not the fastest way of utilizing the GPUs or modern accelerators like TPUs. So replacement for NBConv can be fused NBConv. It's just called, it's funny when you think of context, it's just called fused NBConv because I like to think of it that they fuse these two operations as one. So that's why it's called fused NBConv. So fused NBConv just uses a regular 3x3 convolution. The next thing we've looked at is compound scaling. And the authors have mentioned that compound scaling is not the best way to go, that there might be another way or better way to go. And the last thing that we've looked at so far is progressive resizing. So progressive resizing is just this idea by first introduced in 2018 by Jeremy, that just goes from 2 to 4. First, you train your model on 2 to 4 image size, then you train it on 256, and then you train it on 512. So we've just looked at these 4 things so far. Okay, so then the main contributions of this paper. So when I read this paper first, I just like to read the abstract first and then go into the introduction. So the main contributions are, we introduced this paper called EfficientNetV2. It uses something called neural architecture search. I will show you some context on what that means. They introduced an improved method of progressive learning. I mean, they called it improved method. I kind of disagree with that. I think Jeremy already did all these experiments. He just didn't publish a paper, but this is all, again, things that have been there in the past. And then finally, using these tidbits that have been there, like the fused NBConv in 2019, the progressive resizing in 2018, and bringing them together and taking away the depthwise convolution, this pretty much gets us to EfficientNetV2, which gives us this 11x faster training speed and 6.8x better parameter efficiency. So that's pretty much all there is. I mean, there's not a lot in the EfficientNetV2 paper. If you look at it, I mean, it's just, okay, if I'm a researcher, all I'm doing is I'm looking at, okay, what's new, or what are these things that I can do to improve my network? Okay, in 2018, there was this idea of progressive resizing. Let's try and implement that in EfficientNetV1. Cool, that works. What else can I do? I know that the depthwise convolution doesn't work. So the fused NBConv was released in 2019. Let's try and use that, and let's see if that works. And then when you bring all of these things together, that really gives you the EfficientNetV2 architecture that it is today. And it gets like 85.7%. I'm not making this number up. It's mentioned in this paper somewhere that it gets 85.7% accuracy on ImageNet. So that's a really good high accuracy for convolutional network. So something else I want to touch on is there's a lot of reference for neural architecture search. So why is that? I mean, why is this neural architecture search being used? What's the context of neural architecture search? So the context has been given here in this figure 2, table 3 of the EfficientNetV2 paper. So far we know NBConv is not the way to go. NBConv is slow. It utilizes the GPU like 1% compared to 33% of a regular conv. And what we want to do is we want to replace this NBConv with a fused NBConv. We're going to try and experiment that. And the EfficientNet, this is what the EfficientNet architecture looks like, right? So I'm just going to try and copy paste this. Would it let me? I'm not sure. Okay, it doesn't let me. So anyway, so this is what the EfficientNet, this is the EfficientNet V1. So see how it's using NBConv in all of these stages. It's using NBConv here, NBConv here, pretty much in all of the stages. And we already know we want to replace this NBConv with fused NBConv, right? But how do you replace like a, do you replace all of them with fused NBConv? Like this is another question. Like how do you go about replacing this NBConv with fused NBConv? Do you replace all of them? Do you replace just the first one and everything else remains an NBConv? Or do you replace just the last three with fused NBConv? I'm just going to call it FMC. Do you replace just the last three, or do you just replace the first, fourth, and seventh? Or like what's the combination? Like how do you go about finding the right combination? Because if you go about doing it manually, it's going to take ages because you have all these different combinations that you can try to replace NBConv with fused NBConv. So what's something that the authors did is they tried to replace this NBConv with the fused NBConv in stages. I'm just pasting it here so you can kind of see what's going on. It should let me move it. As you can see, I'm very slow when it comes to these things. But anyway, this is what's happening. So this was the, on your right is this is the EfficientNet V1. And then what the authors are doing is that they first try and replace in stage 1 to 3. So they say, okay, let's replace this in stages 1 to 3. And then what we can see is that if everything remains NBConv, my accuracy is 82.8%. If I replace it just in the first 3 stages, my accuracy goes up. And even though my flops go up, the number of images, so flops are just multiply addition operations, basically. So as I said, the NBConv is not the, it doesn't utilize, I've said this, I think a few times now, but I'll say it again, NBConv doesn't utilize the GPU very well. So when you only have just in EfficientNet V1, just these NBConv layers, you can only go 155 images per second on a V100 GPU. But the minute you replace some of these, you replace these ones with a fused NBConv, your accuracy goes up and you can have more images on your V100. So that's why we want to replace NBConv with fused NBConv, because fused NBConv is faster. So then, okay, they say, okay, that works. I mean, that's a good result, right? But what if I replace from stage 1 to 5? In that case, my accuracy remains the same. Images go slightly up, like from 216 to 223. And the last one is, okay, let's replace everything with a fused NBConv. In that case, the accuracy goes down and the number of images also goes like 206. It's not the highest. So the authors thought, okay, there's no easy way for us to find what a good combination is of using fused NBConv and what's a good combination of using NBConv. So what they said is, let's use neural architecture search. How does neural architecture search look like? Going back to the blog, this is what neural architecture search looks like in general. I'm just giving you general context on what neural architecture search look like. You have your models, you have something called a trainer. So your controller is what controls your model architecture in a way. It's sampling models from a search space. Again, you don't need to know everything about what neural architecture search looks like, but just some context would be helpful. The controller, so let me try and explain this. Again, this is from the Nf-ResNets paper. So there's all these different papers that come together in writing a single paper, and to actually so this is from Nf-ResNets paper. So Nf-ResNets is the paper that used sort of this neural architecture search idea for mobile phones. And EfficientNet V1 simply reuse this same architecture to then have neural architecture search to find. Right now, the question we're trying to solve is what's a good combination of NB-conv and fused NB-conv. So you have this controller. So this, let's say you have all these different models. You have M1, M2, M3, M7, all these different let's call it search space. I'm just trying to simplify this neural architecture search for everybody. This is just a very simple version of neural architecture search. So let's say you have all these different models that basically your search space looks something like this, where in M1 you have just the fused NB-conv in the first layer. In M2 you have in the first to 3. In M3 you have first to 5 or first to 7 or whatever. And then there's all these different operations that you can have. You have like a 3x3 convolution. Like basically you have a lot of things that you can pick and choose from. So your subset looks like this. There's like all of these different things, that all of these different combinations, all of these different components that you can pick and choose. Your trainer will train the model, and then you will check the accuracy and latency, which becomes your objective reward. Then based on this reward, the controller will say, oh, the accuracy is not up to the mark. It's not as good as I want it to be. So let's try a different combination. It would say, okay, even though the accuracy is high, the latency is not that good for me. So let's try a different combination. And then by repeating this process over and over and over again, you come to a architecture that you think that then the controller will say, okay, this is good enough. In this case, my reward function is the highest, my accuracy is good, and my latency is good. So that's this idea of neural architecture search. Like you're no longer designing your network architecture. The deep learning using reinforcement learning, this neural architecture search idea is doing it for you. And then by doing this process, it gives us the EfficientNetV2 architecture. So this is what EfficientNetV2 architecture looks like. So that's it. Like I could just stop right here and I could tell you that's it. That's all that there is to know about EfficientNetV2. But there's like more things. So you can see how now it's using still a combination of fused NB-conv and NB-conv, but you can see that it's using fused NB-conv in the earlier layers. So let me go back to the drawbacks. So one of the drawbacks that we had a look at was this. The depth-wise convolutions are really slow in the early layers. Depth-wise convolutions are used in NB-convs. So to take that away, the new architecture uses fused NB-convs in the earlier layers. So that way you're not even using depth-wise convolution in the earlier layers. So that's been fixed. The next thing was compound scaling. We'll have a look at that very soon. But then this is what the EfficientNetV2 architecture looks like. And this is the process on how this architecture was designed. Taking questions now. So if there's any questions.
Hey Aman, in the fused MBCon in the diagram, there was something called SE. Is that the squeeze and excitation block over there?
Absolutely. That is squeeze and excitation. And if you want to read, for everybody else who doesn't know squeeze and excitation, I somehow keep referring to my blogs because I've just written all about them. There is a squeeze and excitation blog that I've also written in the past. I'll just share this with everybody. So in this squeeze and excitation, it will just show you what squeeze and excitation means. But to answer the question, yes, SE is basically just adding squeeze and excitation. Where did you see that? Sorry, where was the SE? I've forgotten where SE was.
I
Hello?
think it's right
It was
here.
in the it was in the MBCon, that diagram that you were showing, right? Fused MBCon. Where was that?
This one?
There, yeah. No. In the previous slide only. If you go, not slide, sorry. The previous
Over
page.
here in this
There,
one.
yeah.
Yes.
Yeah.
So then what the EfficientNet V2 paper, what the researchers of this paper did, they said, okay, this is what basically fused NB-conv looks like, but let's just add squeeze and excitation to it. So it just adds a bit more computation. Basically, squeeze and excitation is just a way of like adding attention to your network. So then it pays attention to the different channels differently. But for context, again, we're not discussing that today. But yes, thank you. That's a really good question. Are there any other questions so far on how the EfficientNet V2 paper has been designed or what's going on with EfficientNet V2? Interesting to see that TPU cores are slightly slower than GPUs. Oh, that's not a, I don't think that's a, wait, how did, who's commented that, Sangyam, and how is that inference
That
being
was,
made?
so I was just looking at table 3, and I assume this is like an inappropriate comparison because TPU has like more than one course, but this was in table 3.
Oh, this one?
Yes.
So how do you know that? Because TPUs are pretty much having more images per second per core compared
Oh,
to, so I
sorry,
guess
I
this
was
is
reading it
150.
inversely. I thought it was seconds. Sorry about that.
Oh, right. That's okay. I think that's fine.
It's early in the
Yeah,
morning.
that's why I was like, okay, sorry, is the TPU really slower? Because that shouldn't be. Because now with the TPU VMs out, I mean, that's just all the craze that there is today. TPUs are generally meant to be faster. So I think that's a incorrect comment. Anyway, so that's that. So like, to summarize, and there's more in the paper, like they do more ablation studies and they dig deeper into the EfficientNet V2 paper. But to summarize, I think I'll summarize everything that we've sort of learned so far. It looks like this. EfficientNet V1 started with NBconf layers, really fast. So it was fast and accurate. EfficientNet V1 have been in the topmost performing networks, and this is not to take away, this is not to say that efficient V1 was a bad architecture. Efficient V1, if not, was one of the best and highly performing architectures using a convolutional neural network. And in fact, all the latest architectures that you see, like WIT or Kite, or basically all these transformer architectures, or all these new architectures that are coming, even Nf-ResNets, all these latest papers that are coming, they compare with EfficientNet's V1. So this is a really good benchmark, or this was EfficientNet V1 was kind of the king of the jungle for quite some time, and it was used a lot. But the authors thought, okay, there's some things that are wrong. NBconf is slow in the early layers. So what can we do? Let's try and replace this with fused NBconf. And then this gives us rise to the EfficientNet V2 paper that uses fused NBconf in the earlier layers and NBconf in the later layers. So that's how this architecture was born, and the process of finding this EfficientNet V2 architecture was through neural architecture search. So that's just how this design architecture looks like. So that's just the design of this architecture. What we're still missing is the training. How did the authors go about, okay, they designed a new architecture that's perfect. I mean, it's faster, we all know, it's like it can process more images and all that, but how do you then go about training this network? How do you go about training, and how do you go about scaling this network? So note that this EfficientNet V2 architecture that we designed, or the authors designed over here, is a small architecture. But if you want to have a higher accuracy, you want to be able to scale this network in depth, width, or resolution. So then there's two things that are still remaining for us to be answered, is the training and the scaling. So scaling just means making this model architecture bigger. And those are answered here. So then they just say we scale up with few additional optimizations. We restrict the maximum image size to 480. So what they've said is when we're scaling the image resolution, we will not go above 480 as an image size. That's because one of the drawbacks that they found with the EfficientNetV2 paper was that training on very large image sizes is slow. We've seen that in part of the drawbacks. So they said, as part of that drawback, let's do this. Let's not go above 480, as very large images often lead to extensive memory and training speed overhead. That's just the first, like this is again scaling, it's still compound scaling, like they're still scaling the depth, width, and resolution, but in terms of the resolution, they're not going above 480. So that's one of the key differences in EfficientNetV2. The next thing is progressive learning, as I've mentioned. So progressive learning. So this is again part of the training. The answer for this is over here. Progressive learning with adaptive regularization. So what they say with progressive learning is, this is my model. Let's call it EfficientNetV2. Let's just call it for simplicity. Let's train this on 2 to 4 by 2 to 4 for say, if the total epochs are 100, like I want to train this model for 100 epochs. Now let's just train this for 25 epochs on this image size. Then let's just go to 256 by 256 for another 25 epochs. Let's just go to 348, just making these numbers up, but just to show you like how that looks like. 348 by 348 for, and then you finally go 480 by 480. That's not how these images would scale. Like they have a rule on how these image sizes would go up. So this image size would go up based on a rule. That rule is mentioned in algorithm 1. I'm just trying to simplify that process on what progressive learning looks like. So they say, okay, for the next 25 epochs, train on 256 by 256, then 348 by 345 for 225, and then lastly on 480 by 480, because that's the highest you can go. What they say, like what they say their innovation is, you have, in terms of regularization, you have 3 things: dropout, random augment, so it's called rand augment. It's just a data augmentation, and you have mix up. All these 3 things kind of add regularization. So if you don't know what any of these are, again, to give you context, if you go in Tim Docs, sorry, that's not the right place. If you go in Tim Docs, if you go in augmentation, in rand augment, so I'll just copy paste this as well. This will give you an introduction on what random augment looks like and how you can experiment with random augment using the PyTorch image models library. So basically what they said, the key idea, dropout, you just search dropout, you'll find lots of articles, and again, same for mixup, there's plenty of good articles on mixup. So what the idea was, if the regularization here is R0, so this is my regularization, as the image size goes up, what that means is, if the image size is bigger, that means there's more computation. And if there's more computation, that means that my model can sort of overfit, like it has more capacity. Then what you do is you increase the regularization. So it goes R0 plus some number, like let's just call it R1. So this regularization will then go R1. And then you again increase regularization to R2, and then you again increase regularization to R3. There's a very simple rule. It's just basically you have initial plus final minus initial by number of stages. Regularization goes up from initial plus final minus initial by number of stages. That's just increasing the image size, and that's just scaling the regularization based on this rule. So they use this algorithm 1 to train the EfficientNetV2 paper. And this idea of increasing regularization as you're increasing the image size, they termed this as progressive learning. And these are the 3 regularizations as I've already mentioned. That's it. That's really it. In terms of then this progressive training settings, they just say, okay, if you have a look, and if you now go back and read this paper, EfficientNetV2, you can go back and have a look at what this algorithm 1 looks like. And then from that algorithm 1, you can, this table 6 will tell you, okay, EfficientNetV2S looks like this. It goes from 128 to 300 image size, from random augment to 5 to 15, dropout from 0.1 to 0.3, L goes from 128 to 380, and all that stuff. Like, this will all give you the configuration. So now you know what these different architectures look like. If you want to experiment with EfficientNetV2 in code, again, PyTorch, if you want to do it in PyTorch, PyTorch image models is one of the best ways to go about it. You can just say, in PyTorch image models, you can just say something like, you can just say import Tim, and then Tim dot create model, just pass in EfficientNetV2 here. And that's it. That will create your model. So anyway, that's just how Tim works. It's that easy in PyTorch image models. In TensorFlow, I think the original source code is in TensorFlow. So let me try and find that. But that's pretty much it in terms of understanding this paper. So let's have a look at, there it is. So in terms of TensorFlow, in AutoML, EfficientNetV2, this is where you want to go. So let me copy paste that. Cool. That's it. That's EfficientNetV2 paper. Does anybody have a question?
Yeah, I have a question.
Yeah.
So I'm new to, neural architecture search. The thing is that this EfficientNet must have been the reinforcement learning must have been trained on a specific data set, correct?
Keep going.
The search. So, will that be specific to a given data set, or does these neural architecture search algorithms apply across data? So to be more specific, so let's say NASNet V1, for example. So is that used widely as a backbone for most of the algorithms like object detection in general? In practice, how is it applicable?
So neural architecture search is a general concept that can be applied to lots of different data or different model architectures. In terms of backbones, there's a lot of different backbones that are available. So MNASNet was just a mobile architecture. You're free to use a MNASNet backbone, or you're free to use an efficient backbone, or all these different backbones that are available. But to answer the question in terms of reinforcement learning, that's a very general concept.
So, should we run this architecture search on the different data sets? Will that be more efficient, or just using this given architecture on any kind of data?
Because you're trying to optimize on ImageNet. That's just the easiest way to go, because you want to optimize for a certain amount of images. If you're trying to train on if your end goal is to train ImageNet, then you use neural architecture search using ImageNet. If your end goal is to use a medical, then you can try with medical data sets. Personally, I haven't dabbled with neural architecture search much to know that if you want to, I think what you're asking is, if you want to train on ImageNet, then would it make sense to use neural architecture search on ImageNet, medical images, or all these different data sets that are there? I would say personally, from what I've read, that's not common. Like, people, when they're training on ImageNet, they use ImageNet images.
Okay. Okay.
Cool. Does that hope that helps?
Yeah.
Okay.
I also want to just add a comment there. So back in the day when Kaggle didn't have a restriction on GPUs, and I assume this is the reason they added that restriction, I would just try to run something along these lines, and it's quite expensive in terms of GPU hours. So normally you wouldn't even want to think about running a NAS search at all, unless you have just like thousands of free credits and you just want to go through them.
Yeah.
Question, any hypothesis on why fused MBCon for all layers reduces accuracy compared to just using it for the first 3 layers and sticking with NBCon 6? I don't know. That's a really good question. I also was curious about that why would NBCon do that? But that's an open question. I don't have an answer for that. With respect to depthwise, sorry. With respect to depthwise convolutions having less operations but performing poorly the only reliable measure of computer performance is time, less operations does not. Yes, that's a good thing. Like if you, I mean, less multiplication addition operation does not necessarily mean that, uh, does not necessarily mean that it will take like less time, it will be faster on a GPU. So that's a really good comment. It makes sense on progressive scaling, but how do you dynamically scale the depth when to change the network architecture? So I think that's just, again, going back to compound scaling. So what I think that's again very similar to what EfficientNet V1 does. You just add, like, increase the number of blocks. So if you have like 5 blocks, you just make it 10 blocks. But overall, like the structure of those blocks, or a fused NVCon remains fused NVCon. Instead of just one, you have 3 in bigger networks. That's just the way of scaling, and that's again very similar. So they in EfficientNet V2, I think they scaled it exactly the same way as they scaled EfficientNet V1. I need to go back and confirm, but it's that's what I think I read, is that they just scale it the same way as they scaled EfficientNet, because they know that that scaling sort of works for EfficientNet V1, then why change it for V2? It does change the network structure, as in, of course, it's more deeper, it has more layers, but that's the idea. That's why you want to change the network structure to make it deeper, like so it can have more computation. Cool, hope that helps. Taking last question, if there is any.
So I'm still a little unclear on the algorithm 1 table. So
Algorithm 1. This one?
yes, that
Oh,
one, yes.
okay. Okay. Do you want me to try and explain that very quickly?
Yes, please.
Okay, it's very easy. So if you have, let's say you have your minimum image size is 100. So you want to start with a minimum image size of 100. And let's say you want to go to a max image size of 200, right? And let's say you're training in 4 stages. So 4 stages. So the first thing you go is you start with 100. Then the next thing you go is you go 100 plus 200 minus 100 by 4, which is 100, which is 125. Then you go 100 plus twice 200 minus 100 by 4, which is 150, and then you go 175. Like that's how this scaling works. Like that's exactly what this algorithm is saying. You go initial plus final minus initial by m minus 1. Sorry, this should be 3. My bad. So this should be 3. This becomes 133. This should be 3. This becomes 166, and then this becomes 199.9 or something like that. But that's just it. Does that help now?
Yes. And then how do you then calculate the regularization you need to apply?
Oh, same. So see how in this table they have like a minimum and maximum dropout rate. So if you have, let's say they said the 0.1 to 0.3, then you go 0.1 plus 0.3 minus 0.1 by 3, then you go 0.1 plus 2 times 0.3 minus 0.1 by 3, then 0.1 plus 3 times 0.3 minus 0.1 by 3. So this gets cancelled, and then you get whatever. I mean, this is just how you go. So in the end, you're going to 0.3.
Okay, gotcha. So you apply all 3 regularizations all the time. It is just how much you apply varies.
No, it's in the stages, right? So because if you have 100 epochs, you're training it in stages. So the first 25 epochs, you train with the image size of I naught and a regularization of R naught. So this could be 100 and this could be 0.1. In the second stage of 25 epochs, you go image size of 133, and then the regularization becomes whatever the answer is of 0.1 plus 0.2 by 3, basically. So whatever that answer is, then that becomes a regularization. Then in the next 25 epochs, you go image size 166, and then whatever the answer of regularization is. And then in the last 25 epochs, you go 200 and then 0.3 as your regularization. Does that help?
Yes. It's very interesting that they do it in step like this, which doesn't depend upon your loss curves or anything. It actually just goes based on fixed, epochs.
Yeah, totally. But yeah, again, this idea of progressive resizing is not new. Like I've seen this being implemented in the FastAI library before. They just sort of do it in like one step instead of training this first and then reusing the weights. Like it's just one step. Anyway, so that's it for today. If there's any other questions, please feel free to post them at this URL, 1dbe.me/efficientNetV2. And cool, I'll see you guys next week.